93 billion light-years. That's the diameter of the observable universe, the sphere of space we can actually see from Earth, stretching out in every direction until light simply hasn't had time to reach us yet. Inside that sphere, roughly 2 trillion galaxies, each one home to hundreds of billions of stars. It sounds like everything. It sounds like the whole story. But here's what almost nobody tells you when they quote that number: 93 billion light-years isn't the size of the universe. It's the size of the part we're allowed to see. And the difference between those two things, what exists, and what we can ever know exists, might be the strangest fact in all of science. Tonight, we're going to sit with that difference. Slowly. We're going to ask what's actually out there, past the edge of everything visible, and why the answer might be permanently, structurally out of reach, not because we haven't built the right telescope yet, but because the universe itself may have made sure we never could. Let your eyes close if they want to. This is a long one, and there's no rush. Let's start with a question that sounds simple. If the universe is 13.8 billion years old, why is the observable universe 93 billion light-years across, and not just twice 13.8 billion, roughly 27.6 billion? The answer is the first thread we'll pull on tonight, and it has to do with the fact that space itself has been stretching the entire time light has been traveling toward us. A photon that left a distant galaxy 13 billion years ago wasn't just crossing empty space, it was crossing space that has since expanded, carrying the source of that light even farther away by the time we finally see it. So when we look at the most distant thing visible to us, we're not just seeing something 13.8 billion light-years away. We're seeing something that is, right now, roughly 46 billion light-years away, because the universe kept growing during the photon's entire journey. That's the origin of our number. 46 billion light-years in every direction, roughly 93 billion light-years across. It helps to picture this with an analogy, even a slightly imperfect one, because pure numbers this large tend to slide past the mind without leaving much of an impression. Imagine standing at night in an open field, holding a flashlight whose beam can only travel a fixed, limited distance before fading into darkness. You can see everything the beam reaches. You can measure it, study it, walk toward any part of it you like. But the field itself doesn't end where your flashlight beam ends. It simply continues, unlit, unmeasured, entirely real, whether or not your beam happens to reach it. Our cosmic horizon works in something like this way, except the beam isn't light we're shining outward, it's the light that has had time to reach us, traveling inward, from everything that exists. Now sit with that for a moment, because here's where it gets strange. That boundary, the 46 billion light-year edge, isn't a wall. It isn't the edge of the universe. It's the edge of what light has had time to cross since the beginning of everything. Beyond it, there could be more galaxies, more stars, more of exactly the same kind of universe we already know. Or there could be something entirely different. We simply don't know, because no signal from beyond that boundary has ever had time to reach us, and by the physics we currently understand, no signal ever will. This is the first quiet horror of cosmology, if you want to call it that. The universe you can study, measure, and photograph is not the universe that exists. It's a local neighborhood. A single well-lit room in a house whose size we can't determine, because we can never leave the room to look at the walls from outside. Cosmologists have a name for this boundary. They call it the particle horizon, the maximum distance from which light could have reached us since the beginning of time. And crucially, this horizon doesn't expand at the same rate every year. In fact, because the expansion of the universe is accelerating due to something we call dark energy, more and more galaxies are, at this very moment, crossing over a different horizon, one where they become permanently unreachable, their light forever unable to catch up to us, no matter how much time passes. Let's slow down here and actually sit with what dark energy means, because we've mentioned it almost in passing, and it deserves more than that. For most of the 20th century, cosmologists assumed that gravity would eventually slow the expansion of the universe down. All the matter in the cosmos pulls on all the other matter, and that mutual pull should act like a brake, gradually reducing the rate at which galaxies move apart from each other, the same way a ball thrown upward slows as gravity pulls it back. The only real question, in this older picture, was whether there was enough matter in the universe to eventually reverse the expansion entirely, causing everything to collapse back inward in a mirror image of the Big Bang, sometimes called the Big Crunch, or whether the expansion would merely slow, approaching zero without ever quite stopping, leaving a universe that expanded forever, just more and more slowly as time went on. In 1998, two independent research teams, studying a particular kind of exploding star called a Type Ia supernova, found something that didn't fit either of these expected pictures at all. These supernovae are useful to cosmologists because they explode with almost exactly the same intrinsic brightness every time, regardless of where or when they occur, which means their apparent brightness, as seen from Earth, can be used to calculate their distance with real precision. The dimmer they look, the farther away they must be. By comparing that calculated distance to the redshift of their light, a measure of how much the wavelength of light has been stretched by the expansion of space during its journey to us, researchers could reconstruct how the rate of cosmic expansion had changed over billions of years of history. What they found was that distant supernovae were dimmer, and therefore farther away, than they should have been if the expansion were merely slowing down under gravity's pull. The only way to explain the data was if the expansion of the universe had actually been speeding up for the past several billion years, rather than slowing down. Something was pushing space apart, working against gravity's pull, and doing so more and more effectively as time went on. This discovery earned the research teams a Nobel Prize a little over a decade later, and it forced cosmologists to add an entirely new ingredient to their picture of the universe, an ingredient nobody had directly detected, whose underlying nature remains genuinely unknown even now, more than 25 years later. Physicists gave it a deliberately vague name, dark energy. Not because it's dark in the sense of absorbing light, but because it doesn't interact with light or ordinary matter in any way we can currently detect at all, except through its gravitational effect on the large-scale expansion of everything. According to our best current measurements, dark energy makes up roughly 70% of all the energy in the universe. Ordinary matter, everything that makes up stars, planets, and every living thing we know of, makes up less than 5%. The remaining 25% is something called dark matter, a separate mystery entirely, which behaves gravitationally like matter but doesn't emit, absorb, or reflect light in any way we can detect. So the honest, humbling summary is this: roughly 95% of everything in the universe is something we cannot directly see, made of substances or effects we don't fully understand, known to us only through their gravitational influence on the small 5% we can actually study directly. Sit with that percentage for a moment. Everything you have ever seen, every star, every planet, every galaxy and every photograph ever taken, is drawn from a slice of reality that makes up less than 1/20th of everything that exists. The rest is there, shaping the expansion and structure of the cosmos, and we still don't fully know what it is. It's worth sitting a little longer with just how strange dark energy is, even compared to dark matter, because the two are often mentioned in the same breath and yet behave in almost opposite ways. Dark matter, whatever it turns out to be made of, behaves gravitationally the way ordinary matter does. It attracts, it clumps, it helped pull the early universe's tiny density variations into the galaxies and galaxy clusters we observe today. It's mysterious in composition, but familiar in behavior. Dark energy is mysterious in an entirely different, more unsettling way. It doesn't clump at all. It appears to be spread perfectly evenly throughout all of space, at every point, in every direction, never concentrating anywhere the way matter does under gravity's pull. And rather than attracting, it pushes space apart, acting like a kind of built-in pressure inherent to empty space itself, growing in total effect not because there's more of it appearing from anywhere, but simply because there's more space for it to exist within, as the universe continues expanding. This last detail is genuinely strange enough to be worth repeating slowly. As the universe expands, the total amount of ordinary matter and dark matter stays the same, just spread across a larger volume, becoming less dense over time, the way a fixed number of marbles scattered across a growing tabletop become more spread out and thinner in concentration. But the total amount of dark energy doesn't get diluted this way at all. Every new cubic light-year of space that comes into existence as the universe expands appears to carry with it its own, fixed amount of dark energy, meaning the total quantity of dark energy in the universe actually increases as space itself grows, rather than staying fixed or diminishing. This has led some physicists to describe dark energy as a property of empty space itself, sometimes called vacuum energy, the idea that even a region of space containing absolutely no particles, no matter, nothing detectable at all in the ordinary sense, still carries an intrinsic energy simply by virtue of being space, and that this intrinsic energy is what's driving the accelerating expansion we observe. Whether this is the full and correct explanation, or merely a useful placeholder description for something deeper still waiting to be understood, remains one of the most actively debated open questions in all of theoretical physics. There's a strange, quiet symmetry worth noticing here, one that will echo through the rest of tonight's exploration in different forms. Dark matter is invisible because it doesn't interact with light in the way ordinary matter does. Dark energy is invisible because it isn't really a thing scattered through space at all, but seemingly a property of space itself. Two entirely different kinds of hiddenness, layered on top of the third kind of hiddenness we opened tonight's video with, the hiddenness of distance and time, the simple fact that most of the universe is too far away for its light to have reached us yet. 3 separate curtains, each hiding something different, each one gradually being drawn back, slowly, carefully, one careful measurement at a time, by people willing to spend entire careers on questions that may never be fully resolved within their own lifetimes. This is the second quiet horror of tonight's video, laid directly on top of the first. It's not only that there's a horizon we can't see past. It's that even within the small sphere we can see, most of what's actually there is invisible to us in a different sense entirely, not hidden by distance, but hidden by its very nature, present all around us, all the time, in quantities that dwarf everything we can directly observe. And it's this same mysterious dark energy, driving accelerating expansion, that's responsible for our earlier open loop, the strange fact that some galaxies appear to recede from us faster than light. We'll return to unpack that properly in the next chapter, once we've laid a bit more groundwork. For now, just hold both of these horizons gently in your mind at once. The horizon of distance, defined by the age of the universe and the speed of light, and the horizon of composition, defined by how much of everything is made of something we still can't directly detect. Some of the light reaching us tonight, from galaxies billions of light years away, is the last light we will ever receive from those places. Not because they're going to disappear, but because the space between us and them is stretching faster than light itself can cross it, driven by an energy we can measure the effects of, but cannot yet explain. We'll come back to that. It's one of the strangest ideas in modern physics, and it deserves its own careful unpacking later tonight. For now, just hold this thought gently. Everything you have ever seen of the universe, every photograph from every telescope ever built, shows you a boundary, not a wall, but a horizon, the same way the horizon on the ocean isn't the edge of the world, just the edge of what curvature allows you to see from where you're standing. The universe beyond our horizon might look exactly like the universe inside it. More galaxies. More stars. More of the same cosmic architecture, stretching on in a way that never resolves into an edge, the way the surface of a sphere never resolves into an edge no matter how far you walk along it. Or it might not. And that's the question we're going to spend the next several hours turning over, slowly, from every angle we have. Long before anyone had the mathematics to describe an expanding universe, people still had to answer this question in some form. What's out past the stars? What's the edge of everything? The earliest recorded cosmologies didn't really have a concept of beyond at all, in the way we mean it tonight. Many ancient civilizations imagined the sky as a literal solid dome, a fixed shell, sometimes called a firmament, with the stars either embedded in it or shining through small holes in its surface. In this picture, there wasn't a beyond to wonder about, because the dome was the edge. Whatever existed past it, if the question even made sense, belonged to the realm of gods, not geography. The ancient Greeks pushed this picture further, and in some ways, closer to something we'd recognize. Aristotle described a universe built from a series of nested, transparent spheres, with the Earth at the absolute center, motionless, and each sphere carrying a planet, the sun, or the moon around us in perfect circles. Beyond the outermost sphere, the sphere of the so-called fixed stars, Aristotle placed something called the prime mover, not a place, but an unmoved cause, existing outside space and time as we'd understand them, setting all the spheres in motion without itself being part of the physical universe at all. In this Aristotelian universe, the question what lies beyond the stars had, in a sense, already been answered before it was asked. There was no beyond, in a physical sense. The outermost sphere was the edge of physical reality itself. This model held for an extraordinarily long time, nearly 2,000 years, refined and adjusted, but structurally intact, all the way through the medieval period. It's worth pausing on that for a moment. 2,000 years is longer than the entire span of recorded scientific inquiry that followed it. A person born under this cosmology and a person dying under it, many centuries later, would have shared the same basic map of the universe's edge. Later thinkers refined the details considerably. In the 2nd century, an astronomer working in Alexandria produced an extraordinarily detailed mathematical model of these nested spheres, complete with small adjustments, circles riding on circles, called epicycles, to account for the fact that planets don't move across the sky in perfectly smooth, simple paths, but occasionally appear to slow down, stop, and even briefly reverse direction, a phenomenon we now understand as an illusion caused by Earth itself orbiting the Sun and periodically overtaking or being overtaken by other planets in their own orbits. Within the framework of a stationary Earth, this apparent backward motion had no simple explanation, and so extra circles were added, layered on top of the original spheres, to make the mathematics match the observations closely enough for practical use, for calendars, for astrology, for navigation. This model wasn't foolish. It was, in fact, remarkably successful at predicting the positions of planets for many centuries, precisely because enough epicycles, adjusted carefully enough, can approximate almost any orbital pattern reasonably well, even if the underlying picture, a stationary Earth at the center of everything, was fundamentally mistaken. This is worth remembering, because it's a pattern that will recur throughout tonight's exploration. A model can make accurate predictions for a very long time while still resting on a foundational assumption that later turns out to be wrong. The picture didn't crack quietly. It cracked because of a telescope, in the early 1600s, when a series of observations made the old nested sphere model impossible to sustain in its original form. Suddenly there were mountains on the moon, moons around Jupiter, spots on the sun, none of which fit comfortably into a universe of perfect, unchanging crystalline spheres, each supposedly smooth and unblemished. If the moon had mountains, it wasn't a perfect crystalline sphere. If moons orbited Jupiter, then not everything in the heavens orbited the Earth. If the sun had spots that changed and moved, it wasn't the unchanging, perfect object the old model required. And slowly, over the following century, the picture shifted from a bounded, finite cosmos with a hard edge to something else entirely. An infinite, or at least unbounded, space filled with stars scattered in every direction, with no obvious edge at all. This shift wasn't instantaneous or universally accepted at first. It took the accumulated weight of many separate lines of evidence, and the mathematical framework developed to describe gravity as acting between any two masses anywhere, regardless of their position, which made the idea of a special, bounded, Earth-centered universe increasingly difficult to justify on physical grounds. This new picture created its own problem almost immediately, one that took another 2 centuries to resolve, and one that connects directly, in a strange way, to the very question we opened tonight's video with. If the universe is infinite, and filled evenly with stars, then no matter which direction you look, your line of sight should eventually hit a star. Every single point in the night sky, extended out far enough, should intersect a stellar surface. And if that's true, the night sky shouldn't be dark at all. It should be a wall of light, as bright, on average, as the surface of a star, because there would always be one directly in your line of sight, however far away. This is called Olbers' paradox, named after the astronomer who articulated it clearly in the early 1800s, though the puzzle had been noticed by others before him, including, in an early and somewhat different form, by the same astronomer who discovered Uranus. And the paradox sat there, mostly unresolved, for the better part of a century, because nobody had the tools yet to answer the question properly. Various partial explanations were proposed and later shown to be inadequate. The idea that intervening dust might block distant starlight, for instance, fails on closer examination, because any dust absorbing that much light over infinite time would itself heat up and begin glowing as brightly as the stars it was blocking. The eventual resolution, and we're going to sit with this resolution for a while, because it's the real hinge point of tonight's video, is that the universe is not infinitely old. Even if space itself extends forever, light from the most distant stars simply hasn't had time to reach us yet, because the universe began a finite time ago. The night sky is dark not because there aren't enough stars, but because most of them are too far away for their light to have arrived. Notice what just happened there. The resolution to a 200-year-old paradox about infinite space turned out to be, in essence, exactly the same idea we started tonight's video with, a boundary defined not by distance, but by time. A horizon, not a wall. This is the moment cosmology stopped being a question about geography and started being a question about time. And once that shift happened, the modern picture, the one we're going to spend the rest of tonight exploring, became possible for the first time in human history. It's worth adding one more layer to this historical picture before we move forward, because it illustrates something important about how scientific understanding tends to grow, not in a single clean leap, but through a long series of partial answers, each one correcting the last while still leaving something unresolved for the next generation to address. Even after Olbers' paradox was resolved by recognizing the universe's finite age, astronomers in the early 20th century still largely assumed the universe, taken as a whole, was static, unchanging in its overall size, even if individual stars were born and died within it. Albert Einstein himself, having developed a complete mathematical description of gravity in the form of general relativity, found that his own equations, applied to the universe as a whole, naturally predicted that space should be either expanding or contracting, not sitting still. Uncomfortable with this implication, and lacking any observational evidence at the time to support an expanding or contracting universe, he added an extra term to his equations, a kind of built-in repulsive force, carefully tuned to exactly cancel out the effect of gravity on cosmic scales, producing a static, unchanging universe that matched the prevailing assumption of the time. He later called this addition his greatest blunder, once observational evidence for cosmic expansion emerged only a few years afterward, making the extra term unnecessary for the purpose he'd originally introduced it for. And yet, in one of the more remarkable turns in the history of physics, that same mathematical term, essentially set aside as an embarrassing miscalculation for most of the 20th century, turned out to be exactly the kind of ingredient needed to explain the accelerating expansion discovered in 1998, the dark energy we discussed just a few minutes ago. The term Einstein introduced for the wrong reason, and later regretted, may have been pointing at something real all along, just not for the reason he originally intended. It's worth pausing a little longer on how the actual observational evidence for expansion first accumulated, because the story is quieter and more gradual than it's often made to sound, and there's something calming in that slowness. Years before the connection between distance and recession speed was firmly established, an astronomer working with a modest telescope had already begun painstakingly measuring the redshifts of what were then called spiral nebulae, fuzzy, faint patches of light in the sky, whose true nature was still genuinely uncertain at the time. Working alone for the most part, using long photographic exposures that sometimes took all night to gather enough light, he found, one after another, that these nebulae showed redshifts, meaning their light was stretched toward longer wavelengths, suggesting they were moving away from us. Almost all of them. Not one or two anomalies, but nearly the entire set, showing the same pattern, again and again. This was a strange enough result on its own, but it took several more years, and several more independent lines of evidence, to connect this pattern of redshifts to an actual distance measurement, and thereby reveal the relationship between distance and recession speed that would eventually become one of the cornerstones of modern cosmology. The astronomer credited with making that connection combined his own careful measurements of galaxy distances, using those specially useful pulsing stars we mentioned earlier, whose brightness reveals their true distance, with the redshift data gathered by others, and noticed the pattern immediately. The farther away a galaxy was, the faster its light indicated it was receding from us, in a relationship that was, remarkably, close to a simple straight line, when the data was plotted on a graph. It's worth sitting with how modest and painstaking this entire process actually was, in practice. There was no single dramatic moment of discovery, no flash of insight that immediately convinced the entire scientific community. It was years of careful, patient measurement, gathered slowly, one exposure at a time, through telescopes that were, by modern standards, extremely limited, requiring enormous skill and patience simply to capture usable data from objects millions of light-years away. The conclusion that reshaped humanity's entire understanding of the cosmos emerged not from a single brilliant flash, but from years of quiet, careful, repetitive work, gathered patiently, night after night, by people willing to sit with uncertainty for a very long time before the pattern finally became clear enough to trust. There's something worth sitting with in that story, gently, as we move forward tonight. Even our very best physicists, working with our very best mathematics, can end up right for reasons that seem wrong at the time, and wrong for reasons that seem right. The universe doesn't organize itself around what feels intuitive or comfortable to the people trying to understand it. It simply is what it is, and our job, generation after generation, is to keep adjusting our picture, slowly, carefully, as new evidence arrives, not because we enjoy being wrong, but because being willing to be wrong is the only path toward eventually being less wrong than we were before. So let's build the modern picture properly, piece by piece, starting from the beginning, both because it's true chronologically, and because it's genuinely the calmest way to hold all of this in your mind as you drift. Roughly 13.8 billion years ago, as best we can measure, the universe began in an extraordinarily hot, dense state, and has been expanding and cooling ever since. This is what people mean when they say the Big Bang, not an explosion happening at a point within existing space, the way a firework happens at a location, but the expansion of space itself, everywhere at once, with everything that would become galaxies and stars already present in an extremely compressed form. This distinction matters more than it might seem to at first. The Big Bang didn't happen somewhere. It happened everywhere, simultaneously, because space itself is what was expanding. There is no center of the universe that things are flying away from, the way debris flies away from the center of an explosion. Every point in space is, in a meaningful sense, equally the center, and every galaxy sees every other galaxy receding from it, in every direction, regardless of where it's located. This is genuinely hard to picture, and almost every visual metaphor for it breaks down somewhere. But one that holds up reasonably well is the surface of a balloon being inflated, with small dots drawn on it to represent galaxies. As the balloon expands, every dot moves away from every other dot, and there's no single dot that counts as the center of the expansion. The center, if you want to call it that, isn't on the surface of the balloon at all. It's a direction perpendicular to the whole two-dimensional surface, existing outside the space the dots actually inhabit. Now, take that balloon metaphor and add one more layer, which is where things start to bend the mind pleasantly rather than uncomfortably. We don't know if the balloon's surface, that is, the actual shape of the universe, is finite, closing back on itself the way a balloon's surface does, or truly infinite, extending forever in every direction. Both possibilities are mathematically consistent with everything we've measured. The measurements we have so far suggest the universe is very close to what's called flat, meaning parallel lines stay parallel forever, rather than curving back to meet each other, or spreading apart the way they would on a saddle-shaped surface. And a flat universe, in the simplest mathematical sense, is an infinite one. Let's slow down and unpack what flat actually means here, because it's a word borrowed from everyday geometry to describe something considerably stranger than a flat tabletop. Cosmologists describe three basic possible shapes for the universe, based on how space itself curves on the largest scales. A positively curved universe, sometimes called closed, behaves something like the surface of a sphere. If you set off in a straight line and kept going, eventually, given enough time, you'd return to your starting point, having traveled all the way around. In this kind of universe, two initially parallel lines would gradually converge and eventually cross, the way lines of longitude on Earth's surface start out parallel at the equator but meet at the poles. A negatively curved universe, sometimes called open, behaves more like the surface of a saddle, or a Pringle-shaped chip, extended infinitely in every direction. In this kind of universe, initially parallel lines would gradually spread apart from each other, diverging more and more the farther they travel, never meeting, never even maintaining a constant distance. A flat universe sits precisely between these two possibilities. Parallel lines stay exactly parallel, forever, neither converging nor diverging, the way parallel lines behave in the ordinary Euclidean geometry taught in school. And in the simplest version of this scenario, a flat universe, unlike a closed one, has no way to curve back on itself. It simply continues, in every direction, without limit. Measuring which of these three shapes actually describes our universe was, for a long time, one of the most important open questions in cosmology. The measurement itself relies, once again, on that same ancient light we mentioned earlier, the cosmic microwave background, the afterglow from roughly 380,000 years after the beginning, when the universe first became transparent enough for light to travel freely rather than being constantly scattered by a hot, dense fog of charged particles. Tiny variations in the temperature of this ancient light, mapped in extraordinary detail by a series of increasingly sensitive satellite missions over the past several decades, encode information about the geometry of space itself, because the apparent size of these temperature variations, as we observe them today, depends on how light from that era has been bent or stretched by the overall curvature of space during its long journey to us. The results, gathered with increasing precision over multiple missions, consistently point to a universe that is flat, or extremely close to flat, to within a very small margin of measurement error, closer to flat than our instruments can currently distinguish from perfectly flat. This is, itself, a strange and mildly unsettling result, because there's no obvious reason the universe had to come out this way. Of all the possible values curvature could have taken, a value so close to perfectly flat, rather than noticeably curved in one direction or the other, is the kind of result that made cosmologists suspicious there might be some deeper mechanism forcing this particular outcome, which is, in fact, one of several major reasons researchers began seriously considering the idea of cosmic inflation, an idea we're going to return to and unpack thoroughly in the second part of tonight's journey. But set that aside for now, and just sit with the conclusion itself. As far as our best measurements can currently tell, the universe is flat, and a flat universe, in the standard understanding, extends infinitely in every direction. If that's correct, and the universe truly is infinite in extent, then something remarkable follows almost immediately, and it's worth sitting with slowly rather than rushing past. An infinite universe, filled with roughly the same density of matter everywhere on the largest scales, a property cosmologists call homogeneity, confirmed by surveys mapping the positions of millions of galaxies across enormous volumes of space, contains infinitely more galaxies than the 2 trillion we can currently see. Not just a little more. Not 10 times more, or 1,000 times more. Infinitely more. Our observable universe, that 93 billion light-year sphere we opened with, would be an infinitesimally small sample of the whole, the way a single drop of water is an infinitesimally small sample of an ocean that has no far shore at all. And here's the detail that tends to unsettle people most, once they really absorb it. In an infinite universe with roughly uniform properties, statistically, everything that can happen, does happen, somewhere. Not as a mystical claim, but as a mathematical consequence of infinite repetition. Given infinite space and a finite number of ways atoms can be arranged into stars, planets, and even entire galactic superclusters, every possible arrangement that isn't physically forbidden will occur again and again, infinitely many times, scattered across distances so vast that no signal, no light, no information of any kind could ever travel between one occurrence and the next. Some physicists have taken this idea seriously enough to calculate a rough distance at which you'd expect to find, statistically, an exact copy of our observable universe, every galaxy, every star, arranged identically, purely by chance. The way a coin flipped enough times will eventually land on the same 20 flip sequence twice. The numbers involved are so large they stop feeling like real distances at all. They're not numbers you're meant to picture. They're numbers meant to communicate a kind of scale that human intuition was never built to hold. We are not going to try to hold that number tonight. What we're going to hold, instead, is the shape of the idea, that what we call the universe, the thing astronomers study, photograph, and write papers about, is very likely a local reading, taken from one small region of something enormously larger, the way a thermometer reading in one city tells you something true, but very incomplete, about the climate of an entire planet. Before we move to how we actually measure any of this, it's worth pausing on just how counterintuitive it is that flat could ever mean infinite in the first place, because the everyday word does a poor job of preparing you for the cosmological one. In ordinary usage, flat suggests something small and bounded, a flat tabletop, a flat sheet of paper, a flat field you could walk across in an afternoon. None of these things are infinite. So it can feel like a kind of linguistic trick when cosmologists say the universe is flat and mean, by that word, something that stretches on forever. But the mismatch is really just a mismatch of scale and context, not a contradiction. A flat sheet of paper is flat locally, at the scale of the paper, but it still has edges, because it's a small, finite object embedded in a larger three-dimensional space. What cosmologists mean by a flat universe is different. It's a statement about the intrinsic geometry of space itself, at every scale, with no larger space for it to be embedded within at all, and no edges anywhere, because there's nothing outside it for an edge to face. This is worth sitting with slowly, because it's the kind of idea that resists being pictured directly, the way most deeply true things about the universe tend to resist easy pictures. We're used to thinking about shapes as objects sitting inside some larger space, a ball sitting in a room, a sheet of paper lying on a table. But the universe, under this framework, isn't an object sitting inside some larger container at all. It simply is the container, in its entirety, and asking what it's flat within, or what surrounds it, may be a question built on the same kind of a category error as asking what's north of the North Pole. Not unanswerable because the truth is hidden from us, but unanswerable because the question, once you trace it carefully enough, stops pointing at anything coherent at all. Let's linger a while longer on how we actually know any of this, because the measuring itself is almost as remarkable as what it reveals. The cosmic microwave background we've mentioned a few times now isn't just a convenient historical curiosity. It's arguably the single most important piece of evidence in all of modern cosmology, and it's worth understanding, gently and slowly, exactly what it is and why it exists at all. In the earliest moments after the beginning, the universe was far too hot for atoms to exist in any stable form. Any electron that happened to bind to a proton would immediately be knocked loose again by the sheer density of light and heat surrounding it. This meant that space itself was filled with a hot, opaque plasma, a dense fog of charged particles and light, constantly scattering off each other, unable to travel freely in any direction for any meaningful distance. Light in this era behaved the way light behaves inside a thick cloud, or inside the sun itself even today, constantly absorbed and re-emitted, trapped, unable to stream outward in a straight line. This continued for roughly 380,000 years, which sounds like an enormous span of time in human terms, but is a mere fraction of the universe's total age so far. As the universe expanded during this period, it also cooled, and eventually it cooled enough that electrons and protons could finally combine into stable, neutral atoms, mostly hydrogen, with a smaller amount of helium, without immediately being torn back apart by ambient heat. The moment this happened, called recombination, the fog lifted almost instantly, on cosmic timescales. Light that had been trapped, scattering endlessly, was suddenly free to travel in straight lines, uninterrupted, for the first time since the beginning. That light is still traveling. Right now. In every direction. And some of it, having journeyed for nearly the entire age of the universe, is arriving at Earth at this very moment, detectable not as visible light anymore, because the expansion of space has stretched its wavelength enormously over billions of years, but as faint microwave radiation, barely a few degrees above absolute zero, filling the entire sky almost perfectly evenly in every direction we point an instrument. This is genuinely one of the most beautiful facts in all of science, if you let it settle properly. We are not simply calculating what the early universe might have looked like, from theory alone. We are directly observing light that was emitted 13.8 billion years ago, from the moment the universe first became transparent, arriving at our instruments tonight, carrying information from a period so early that essentially nothing else from that era survives in any directly observable form. And within that faint, ancient light, cosmologists have found something extraordinary: it isn't perfectly uniform. There are tiny variations in temperature, differing from one point in the sky to another by only a few parts in 100,000, an almost imperceptibly small ripple, layered on top of an otherwise remarkably smooth glow. These tiny variations are not noise or measurement error. They are, in fact, the single most important piece of data we have about the structure of the early universe, because they represent the seeds from which every galaxy, every star, every planet, and every living thing would eventually form. The regions that were very slightly denser than average, by the tiniest of margins, exerted very slightly more gravitational pull on their surroundings. Over hundreds of millions of years, that tiny extra pull attracted more and more matter, which increased the gravitational pull further, in a slow, self-reinforcing process that eventually produced the enormous cosmic web of galaxies and galactic clusters we observe today, strung together like a vast, three-dimensional net across billions of light-years of space. Mapping this cosmic web directly has become one of the major projects of modern astronomy. Enormous surveys, using dedicated telescopes built specifically for this purpose, have measured the precise positions and distances of literally millions of galaxies, building up a three-dimensional map of the observable universe layer by layer, the way a doctor might build up a full picture of the body through many individual slices of a medical scan. These surveys have confirmed, again and again, at ever-increasing scales and precision, that the universe really does look the same in every direction, and really does have roughly the same density of galaxies everywhere, once you average out over large enough volumes, a property that would be a very strange coincidence indeed if the universe had some kind of special center or edge nearby that we simply hadn't noticed yet. All of this, the ancient light, the tiny temperature variations, the enormous surveys of galaxy positions, points toward the same conclusion from several genuinely independent directions at once, which is part of why cosmologists trust the overall picture as strongly as they do. It's not resting on a single measurement, or a single clever calculation. It's resting on multiple, separate lines of evidence, developed by different research groups using different instruments and different methods, all converging on the same basic answer: a flat, or very nearly flat, universe, filled with only a small fraction of ordinary matter, expanding at an accelerating rate, extending outward at least as far as we can measure, and quite possibly, if the flatness holds exactly, extending forever. There's one more piece of this geometric puzzle worth sitting with slowly, because it connects directly to that suspicious closeness to flatness we mentioned a moment ago, and it's going to matter a great deal once we reach the second half of tonight's journey. If the universe's overall density, the total amount of matter and energy packed into any given volume of space, sits exactly at a particular value, called the critical density, then the geometry comes out exactly flat, with parallel lines extending forever without converging or diverging. If the density is even slightly higher than this critical value, the universe curves back on itself, closed, finite, eventually returning to its starting point if you travel far enough in any direction. If the density is even slightly lower, the universe curves the other way, open, infinite, with parallel lines spreading apart from each other without limit. Here's the part that unsettled cosmologists enough to go looking for a deeper explanation. For the universe to appear as close to flat as our measurements show it to be, today, after 13.8 billion years of expansion, the density in the extremely early universe would have needed to match the critical value to an almost unbelievable degree of precision, differing from the critical value by less than one part in many, many trillions, at the earliest moments we can meaningfully calculate. Any larger deviation, even a seemingly tiny one, would have been dramatically amplified over billions of years of subsequent expansion, producing a universe that looked obviously and strongly curved today, in one direction or the other, rather than the strikingly flat universe we actually observe. This is sometimes called the flatness problem, and it's exactly the kind of puzzle that suggests something is missing from the simplest possible picture, some additional mechanism, operating very early in cosmic history, that would naturally push the density toward the critical value, rather than requiring an almost impossibly precise coincidence in the initial conditions of the universe. We're going to meet that mechanism properly in the second half of tonight's exploration, and it's going to turn out to be the very same idea responsible for the strange, uniform temperature of that ancient light we discussed earlier, the idea of cosmic inflation, an extraordinarily brief but extraordinarily powerful burst of expansion in the earliest moments after the beginning, capable of flattening out almost any initial curvature, the way stretching a small, wrinkled patch of paper flattened. Taut removes any small-scale bumps or curves it might have started with, leaving something that looks, at least locally, essentially flat, regardless of what shape it might have had before the stretching began. Hold that thought gently. We're not ready to unpack inflation fully yet. That's coming, patiently, in due course. For now, it's enough to simply notice that the flatness we've measured, the flatness that implies an infinite universe extending endlessly beyond our horizon, might itself be a clue, a fingerprint left behind by something that happened in the very first instance of everything, long before galaxies, long before stars, long before even atoms existed in any stable form at all. Let's slow down here, because this is a good place to just sit with what we've built so far, before we add the next layer. We started with a boundary, 46 billion light-years, in every direction, defined not by a wall, but by the age of the universe and the finite speed of light. We saw that this boundary has been shifting throughout history, from a solid crystal sphere in the ancient world, to an unresolved paradox about infinite starlight in the 1800s, to a horizon defined by time itself in the modern era. We learned that most of what fills this vast volume isn't even the ordinary matter we can see and study directly, but something else entirely, still poorly understood, making up the overwhelming majority of everything that exists. And now we've arrived at the strange, quiet possibility that whatever lies past this first horizon might not just be unknown, it might be effectively infinite, repeating the same handful of physical patterns over and over across distances too large to meaningfully picture. If you're starting to feel a little bit small right now, that's completely appropriate. Let that feeling settle rather than resisting it. There's nothing to solve here, nothing to fix. Just space to notice, and rest inside. Let's return to that first open loop from the very beginning of tonight's video, the strange fact that the most distant galaxies we can see appear to be receding from us faster than the speed of light. This sounds like it should be impossible. Nothing, according to Einstein's physics, can move through space faster than light. And yet cosmologists talk about superluminal recession as an ordinary, uncontroversial fact. How can both of these things be true at once? The resolution is subtle, but once it clicks, it stays clicked. So let's take it slowly. The speed limit of light applies to things moving through space. It does not apply to the expansion of space itself. A galaxy sitting still, relative to the space immediately around it, isn't moving in the sense the speed limit restricts, but if the space between that galaxy and us is stretching, the distance between us can grow faster than light, without either of us actually moving through space in the traditional sense at all. Think of it this way. Two dots drawn on the surface of that balloon we talked about earlier aren't moving across the balloon's surface. But if you inflate the balloon fast enough, the distance between those two stationary dots can increase at any rate at all, with no upper limit, because it's the surface itself expanding, not the dots moving across it. This is exactly what's happening with distant galaxies. Beyond a certain distance, a boundary called the Hubble radius, a slightly different horizon from the particle horizon we discussed earlier, galaxies are receding from us faster than light, purely because of the cumulative stretching of the space between here and there. Nothing local is being violated. Locally, in any small patch of space, light still moves at the same, unbreakable speed. It's only the accumulated stretching across enormous distances that produces a recession speed greater than light. And here's the consequence that matters most for tonight's larger question. Any galaxy currently beyond the Hubble radius, receding from us faster than light, can send light toward us all at once, and that light will never arrive. Not eventually. Not after a very long wait. Never. The space between us and that galaxy is growing faster than the light can close the distance. The way a person walking toward you on a travelator moving away from them faster than they can walk will never actually reach you, no matter how long they keep walking. Some of these galaxies are visible to us right now, because the light we're seeing left them a very long time ago, before they crossed this boundary. But that light is, in a real sense, the last message we will ever receive from them. As the universe continues expanding, and it's not just expanding, but accelerating, due to the dark energy we discussed earlier, more and more galaxies are crossing this boundary, becoming permanently, physically unreachable, their future light forever unable to catch up to us. There's a genuinely strange implication buried in this. In the very distant future, trillions of years from now, far beyond the current lifespan of any star we know, an observer looking out from what remains of our galaxy would see almost nothing beyond it. Every other galaxy would have crossed this horizon, their light having stopped arriving long ago. The night sky, for that far future observer, would be almost completely dark and empty, not because the rest of the universe stopped existing, but because it had drifted permanently beyond the reach of any signal at all. We are living, right now, in an unusually favorable moment for cosmology, a window of time in which distant galaxies are still visible, their light still arriving, before that window slowly, gently closes. Future civilizations, if they exist far enough ahead of us, may look out at a sky that gives them almost no clues at all that an expanding universe full of other galaxies ever existed. They might reasonably conclude, from their observations alone, that their galaxy is the only one there has ever been. That's worth pausing on. We may be living inside one of the only eras in the vast future history of the universe during which the true scale of the cosmos is still visible and knowable at all. Let's slow down and unpack the actual mechanics of how we detect this recession at all, because it connects back to something we touched on briefly earlier, the stretching of light itself, called redshift. When a source of light moves away from an observer, or when the space between a source and an observer is expanding, the light's wavelength gets stretched in the process, shifted toward the longer, redder end of the visible spectrum, and beyond it, into infrared and eventually microwave wavelengths for light that has traveled far enough, through enough expanding space. This is directly analogous, in a rough sense, to the way a siren sounds lower in pitch as an ambulance drives away from you. The sound waves are stretched by the motion, the same way light waves are stretched by the expansion of space. By carefully measuring exactly how much a distant galaxy's light has been shifted toward the red end of the spectrum, astronomers can calculate, with real precision, how much the universe has expanded since that light was emitted. A galaxy whose light has been stretched to twice its original wavelength tells us that the universe has expanded to twice its size, in the relevant sense, since that light began its journey. A galaxy whose light has been stretched by a factor of 10 tells us the universe was 10 times smaller, overall, when that light left its source. This gives astronomers an extraordinarily powerful tool. By measuring redshift alone, without needing to independently measure distance through any other method, they can determine how much cosmic expansion has occurred since any given beam of light was emitted. And by combining redshift measurements with distance measurements obtained through other means, including those special exploding stars we discussed earlier, whose true brightness is known and can be compared against their apparent brightness to calculate distance, cosmologists can reconstruct the entire expansion history of the universe, layer by layer, going back further and further in time as they study more and more distant, and therefore more and more ancient, sources of light. This is also, in fact, precisely how the Hubble radius itself is calculated. Cosmologists know the current rate of cosmic expansion, a number called the Hubble constant, which describes how much any given volume of space is stretching per unit of time, and by working out at what distance this stretching accumulates to match the speed of light itself, they arrive at a specific figure, roughly 14.4 billion light-years. Beyond that distance, right now, at this very moment, the cumulative stretching of space between us and anything located there exceeds the speed of light, even though nothing local is moving that fast, and even though light itself still travels at its ordinary, unchanging speed within any small region of space. It's worth noting that this Hubble radius, 14.4 billion light-years, is considerably smaller than the particle horizon we discussed earlier, the 46 billion light-year boundary that defines the edge of the observable universe. These are two genuinely different boundaries, describing two different things, and it's easy to conflate them if you're moving quickly, so let's take a moment to separate them clearly. The particle horizon describes the maximum distance from which light could have reached us at all, given the entire age of the universe. It's a statement about the past, about what light has had time to arrive from since the very beginning. The Hubble radius describes the current boundary beyond which recession speed exceeds the speed of light right now. It's a statement about the present moment, about what's happening to space at this instant, rather than about the total accumulated journey of any particular beam of light. Here's the genuinely strange part, worth sitting with slowly. Some galaxies located beyond the current Hubble radius are still visible to us, and some of their light is still arriving, even though those same galaxies are, right now, receding from us faster than light. This isn't a contradiction, once you remember that the Hubble radius describes present moment recession speed, not the total journey of light that was emitted long ago, potentially before that galaxy crossed over the boundary, or even if it emitted that light while already beyond the boundary, under certain specific conditions related to how the expansion rate itself has changed over cosmic history. This is genuinely subtle physics, and professional cosmologists sometimes disagree about the clearest way to explain the details to a general audience, precisely because the interplay between these different horizons, and the changing rate of expansion over time, produces a genuinely complicated picture once you try to trace the exact path of any individual beam of light through the entire history of cosmic expansion. But the core takeaway, the one worth carrying forward into the rest of tonight's exploration, is simple enough to hold gently. there are multiple different horizons, multiple different boundaries, layered on top of each other, each one describing a slightly different kind of limit on what we can observe, and each one shifting, slowly, as the universe continues to age and expand. Let's slow all the way down here for a moment. There's no need to rush toward the next idea. Let this one breathe. Let's take a few final, quiet minutes here, at the close of this first part, to simply let everything settle, without adding anything new. We began with a number, 93 billion light-years, and learned that it describes a horizon, not a wall. We followed that horizon backward through history, from a solid crystal dome, to an unresolved puzzle about a dark night sky, to a horizon defined, finally, by time itself. We learned that almost everything filling this enormous volume of space is something we still cannot directly detect or explain, an invisible 95% of everything, shaping the expansion and structure of the cosmos from behind an unlit curtain we've only recently learned is even there at all. We measured the shape of space itself, using light older than almost everything else we will ever study, and found it flat, or close enough to flat that the difference may not be measurable at all, implying, if the simplest interpretation holds, a universe that does not end, extending forever in every direction, filled with more of everything than we could ever count or name. And we found, sitting quietly underneath all of it, two open questions we haven't fully answered yet. Why light from far enough away can never catch up to us, no matter how long it travels. And whether anything we cannot ever observe can be said to exist at all, in any sense that matters. Those two questions are exactly where the second half of tonight's journey will begin. We'll trace the discovery of cosmic expansion in more detail, follow the mathematics of inflation into its strangest and most far-reaching implications, sit with the idea of other universes entirely, ask carefully whether beyond even means anything at all, and close, gently, with the one loophole physicists have seriously proposed for glimpsing something past our own horizon. Before we go further out, into ideas about what might lie beyond the horizon altogether, it's worth pausing on how strange and recent all of this really is. Until the 1920s, most astronomers, including very serious ones, assumed the universe was static, unchanging in its large-scale structure, roughly the same size and shape it had always been, with the Milky Way essentially constituting the entirety of everything. The idea that there might be other galaxies at all, distinct island universes far beyond our own, was genuinely controversial well into the 20th century, debated formally in a famous scientific exchange sometimes remembered as the Great Debate, held before a general audience, with two respected astronomers arguing opposite sides of the very same question we've been circling all night. Is there more out there, or is what we can see already everything? It's worth sitting a little longer with the actual shape of that debate, because it wasn't a quiet, private disagreement between two colleagues, but a genuinely public argument, staged before a general audience, at a time when the question still felt entirely open. One side argued that the Milky Way constituted essentially the entire universe, with those fuzzy, faint patches of light being small, nearby clouds of gas or young star clusters within our own galactic structure. The other side argued that at least some of these fuzzy patches were vastly more distant, entire separate galaxies in their own right, comparable in size to the Milky Way, situated millions of light-years away. Both astronomers marshaled genuinely serious evidence for their positions, using the best data and reasoning available at the time, and neither side's argument was foolish or hastily assembled. This is worth remembering, because it's easy, from the comfortable position of hindsight, to imagine that the correct answer should have been obvious all along, and that anyone arguing the other side must have been careless or mistaken in some easily spotted way. The reality was messier and more honest than that. The data available at the time was genuinely ambiguous, capable of supporting either interpretation depending on which specific measurements you weighted most heavily, and it took several more years of careful, patient observation, that painstaking work with pulsing stars we discussed earlier, before the question was finally settled, decisively, in favor of the larger, multi-galaxy universe. It took careful measurements of a particular class of star, one whose brightness pulses in a very regular, predictable rhythm, allowing its true distance to be calculated from how bright it appears compared to how bright it actually is, to settle the question. When those measurements were finally made on stars inside a fuzzy patch of light long assumed to be a nearby cloud of gas within our own galaxy, the distances that came back were staggering. That patch of light wasn't a nearby cloud at all. It was an entire separate galaxy, over 2 million light-years away, containing hundreds of billions of stars of its own, comparable in scale to the Milky Way itself. And then, almost immediately after establishing that other galaxies existed at all, astronomers noticed something even stranger. Nearly all of them appeared to be moving away from us, and the farther away a galaxy was, the faster it appeared to be receding. This relationship, distance correlating directly with recession speed, became the first solid observational evidence that the universe itself was expanding, rather than simply being a fixed, static backdrop that galaxies happen to move around within. It's genuinely remarkable how recent this is. Your grandparents' grandparents could have been alive during a period when serious scientists debated whether other galaxies existed at all. The expanding universe, the entire framework we've been building across both parts of tonight's journey, is barely a century old as an accepted scientific fact. Compare that to the 2,000 years the crystalline sphere model held its ground, and you start to get a sense of just how quickly our picture of the cosmos has been rewritten, again and again, each time revealing something larger and stranger than what came before. There's a pattern here worth noticing, because it's going to matter again before tonight is over. Every single time humanity has settled comfortably into a picture of the universe, a bounded set of crystal spheres, a static eternal cosmos, even the modern picture we've built so far tonight, that picture has eventually been shown to be too small. Not wrong, exactly, in every detail, but incomplete in a way that only became visible once better tools or better mathematics arrived. It's worth sitting with what that period of transition must have actually felt like, for the people living through it, because it's easy, looking back with the comfort of hindsight, to imagine the shift from a static, single-galaxy universe to an expanding, multi-galaxy one as a clean, tidy update, a single new fact slotted into an otherwise unchanged picture. It wasn't like that at all, for the people experiencing it in real time. It meant discovering, within a single professional lifetime, that the entire visible universe they'd been trained to study was a small fraction of something enormously larger, and that the larger thing wasn't sitting still, but rushing apart, carrying everything within it toward a future no one yet had any framework for predicting. Some astronomers of that era described the discovery, in their own private writings, with something closer to unease than triumph, a sense that the universe had turned out to be far stranger and far less anchored than they had spent their careers assuming. Keep that feeling in mind as we move into the next section, because it's about to happen again, and this time, the thing that turns out to be too small is the very idea of the universe itself. So far, everything we've discussed assumes there's one universe, expanding from one beginning, with one set of physical laws that applies everywhere within it, all the way out to whatever infinite or finite extent it turns out to have. That's already an enormous, humbling picture. But there's a further possibility, taken seriously by a meaningful portion of the physics community, that even this picture might be too small. To understand why, we need to go back to the very beginning again, not the Big Bang as a single event, but a specific idea about what happened in the first unimaginably small fraction of a second afterward, called cosmic inflation. The basic problem inflation was designed to solve is one we've actually already touched on in part 1. The strange, almost suspicious uniformity of that ancient light, the cosmic microwave background, which shows nearly identical temperatures across the entire sky, in every direction, even between regions so far apart that, under ordinary expansion alone, they should never have been able to exchange heat or light at all. And alongside that puzzle sits the flatness problem we discussed as well, the strange precision with which the early universe's density matched the exact value needed to produce the flat geometry we measure today. The solution proposed in the early 1980s, and refined considerably since, is that in an extraordinarily brief period right after the beginning, lasting perhaps a tiny fraction of a second, the universe underwent an enormous, exponential burst of expansion, far faster than the ordinary expansion that continued afterward. During this burst, a tiny region of space, small enough that it had time to reach a uniform temperature through normal contact, was stretched by an almost inconceivable factor, becoming the seed of everything we now observe. The temperature uniformity we see today is a fossil of that one tiny, uniform patch, stretched out to cosmic scale. And the flatness we measure today is a fossil of the same process, for the same underlying reason a small, wrinkled patch of paper looks perfectly smooth once you've stretched it out enormously. Any initial curvature simply gets diluted toward flatness by a large enough expansion, regardless of what shape it started with. This idea, called inflation, solved several deep puzzles at once and made a number of very specific, testable predictions that have since been confirmed to a striking degree of precision by satellite measurements of that same cosmic microwave background, including subtle details about the exact statistical pattern of those tiny temperature variations we discussed earlier, details that match inflation's predictions with real precision. It's not a fringe idea. It's a central pillar of modern cosmology, even though the exact physical mechanism driving it, the specific field of energy responsible, remains an area of active, unresolved research. But inflation carries with it a strange and largely unavoidable consequence, once you follow the mathematics carefully. The physical process that drives inflation, a field of energy that causes space to expand exponentially, doesn't necessarily stop everywhere at the same moment. In most versions of the theory, inflation ends locally, in patches, while continuing elsewhere. Our observable universe, in this picture, is just one patch where inflation ended, allowing ordinary matter, stars, and galaxies to form. But the underlying inflating field, in the space beyond our patch, may still be expanding, forever, endlessly spawning new patches where inflation ends locally and a new pocket universe begins. This idea has a name, eternal inflation. And the pocket universes it produces are sometimes called bubble universes, regions where inflation has ended, floating within a vastly larger, eternally inflating background, the way bubbles form and separate within a pot of boiling water, each one its own self-contained region, expanding within, forever surrounded by more inflating space that may be producing more bubbles, without end, in every direction, without any process that would ever stop it. It's worth sitting with the actual mechanics of why inflation, once it starts, tends to continue forever in at least some regions, rather than simply ending everywhere at once the way you might naively expect. It's worth sitting a little longer with why this runaway process is described as eternal rather than simply very long, because the distinction matters for how we picture the overall structure. In an eternally inflating background, at any given moment, there is always some region still undergoing inflation, no matter how far into the future you look, because the volume being added by expansion always outpaces the volume being converted into ordinary bubble universes. This means the process, once started, has no natural endpoint at which it exhausts itself entirely. Individual bubbles form, age, and in principle could eventually experience their own version of a distant future, but the larger inflating structure surrounding them continues indefinitely, producing new bubbles at every subsequent moment, forever, without any mechanism that would bring the entire process to a close. This creates a strange asymmetry worth noticing. From the perspective of any single bubble, like our own, the inflating background looks like something that happened before us, an ancient process that ended locally to produce our universe roughly 13.8 billion years ago. But from the perspective of the overall structure, that same inflating background is not a past event at all, it's an ongoing, continuously unfolding process, happening right now, in an ever-expanding sea of space surrounding our own small pocket, exactly as active today as it was at the moment our own bubble formed. The field driving inflation behaves, in a rough sense, like a ball balanced very precisely near the top of a hill, rather than sitting comfortably at the bottom of a valley. While it remains near the top, its energy drives the exponential expansion. Eventually, in any given region, quantum fluctuations, small, random jitters inherent to any field at the smallest scales, nudge the field down off the top of the hill, ending inflation locally and releasing its stored energy into the ordinary matter and radiation that would go on to form stars and galaxies. But here's the crucial detail. The exponential expansion happening during inflation is so fast that it can outpace the rate at which any given region rolls down off the hill and ends. This means that even as some regions are ending inflation, becoming ordinary pocket universes like our own, the overall volume of space still undergoing inflation continues to grow, faster than it's being converted into ordinary universes, simply because expansion adds volume so much more quickly than the ending process can consume it. The result is a kind of runaway process. Inflation, once started, essentially never fully stops everywhere, even though it does stop in an ever-growing number of individual pockets, one of which, at some specific moment roughly 13.8 billion years ago, became everything we've spent both parts of tonight discussing. If this picture is correct, and it's important to be honest that this remains a genuinely open, actively debated area of physics, not a settled fact the way the expansion of our own universe is, then the universe we've spent this entire journey discussing might itself be a single bubble. One pocket among an uncountable, perhaps literally infinite, number of other pockets, each one potentially governed by different physical constants, different rules, different versions of the laws we've built our entire understanding of tonight upon. This last detail deserves its own careful unpacking, because it's one of the more genuinely mind-bending implications of the whole framework. The specific values of certain fundamental numbers in physics, the relative strengths of the basic forces, the precise mass of certain particles, the exact value of that dark energy we discussed at length in Part 1, don't appear to be required to take the particular values they do by any deeper mathematical necessity we've yet discovered. They simply are what they are, measured carefully, plugged into our equations, without a clear answer to the deeper question of why those specific numbers, rather than some other set entirely. Some physicists have proposed that if eternal inflation is correct, different bubble universes might settle into different possible values for these numbers, the way a ball rolling down a bumpy hillside with many separate valleys might come to rest in any one of them, depending on small, essentially random details of its initial trajectory. Under this view, our particular universe's constants aren't fine-tuned by any special mechanism at all. They're simply the values that happen to produce a universe capable of forming stars, atoms, and eventually life, and we observe those particular values not because they are special in some deeper cosmic sense, but because we could only ever exist to ask the question within a bubble whose constants happen to permit our own existence in the first place. Other bubbles, with different constants, might be entirely lifeless, or governed by physics so different that concepts like atom or star might not even meaningfully apply. It's worth pausing on a specific, well-known example of this fine-tuning puzzle, because it illustrates just how strange these coincidences can appear once you look closely at them. The strength of the dark energy we discussed at length in Part 1, the mysterious force driving accelerating expansion, appears, when calculated from basic quantum theory, to want to take an absolutely enormous value, many orders of magnitude larger than what we actually observe. If dark energy really did take the value naive theoretical calculations suggest it should, the resulting expansion would have been so overwhelmingly powerful that it would have torn apart any early clumps of matter before they ever had a chance to collapse into stars or galaxies at all. In such a universe, nothing like us, and nothing resembling any observer capable of even asking these questions, could ever have formed. Instead, the dark energy we actually measure is dramatically, almost absurdly smaller than this naive theoretical expectation, small enough to permit the graceful, patient 100-million-year process of gravitational collapse that built the stars and galaxies we've spent this entire journey discussing, without being so small that the accelerating expansion we detected in 1998 wouldn't happen at all. This specific value has been described, by more than one physicist working in the field, as one of the most severe and unexplained fine-tuning problems in the entirety of theoretical physics, a value that seems to sit in an extremely narrow window, compatible with the existence of anything resembling us, without any settled explanation for why it landed precisely there rather than anywhere else along an enormous range of possible values. The anthropic reasoning we've been discussing offers one possible resolution to this specific puzzle. If there are enormously many separate bubble universes, each with its own randomly assigned value for dark energy, then most of those bubbles would indeed be lifeless, torn apart or crushed by expansion values incompatible with any complex structure forming at all. But a small fraction, purely by chance, would land in that narrow habitable window, and, unsurprisingly, it's only within that small fraction that anyone would ever exist to notice the coincidence and wonder about it. Under this reasoning, we don't need a deep, specific physical mechanism explaining why our particular bubble got such a small, life-permitting value. We simply need enough bubbles, with a broad enough range of random values, for at least one of them, statistically, to land in the narrow window that permits observers, and naturally, we find ourselves living precisely within that fortunate bubble, because we couldn't exist anywhere else. This is, understandably, a deeply unsatisfying answer to some physicists, even those who accept its logical validity, because it explains a specific number not by deriving it from some deeper principle, the way physics has traditionally made progress, but by appealing to a kind of cosmic lottery combined with an unavoidable selection effect. Critics of this approach worry, reasonably, that it risks becoming an all-purpose explanation for any otherwise puzzling fine-tuning, discouraging the search for a more specific, satisfying mechanism that might genuinely explain why our universe's constants take the values they do, rather than simply shrugging and appealing to the sheer number of alternative possibilities we happen not to inhabit. It's worth briefly noting one more example of this same kind of fine-tuning puzzle, distinct from dark energy, because it shows the pattern isn't confined to a single quantity. The relative strength of the nuclear force that binds atomic nuclei together, compared to the electromagnetic force that pushes protons apart, sits in a fairly narrow range that permits stable atoms heavier than hydrogen to exist at all, including the carbon that forms the backbone of every known form of life. A meaningfully stronger or weaker nuclear force, relative to electromagnetism, would either prevent complex atoms from forming, or make stars burn through their fuel so quickly and unstably that the billions of years needed for life to evolve would never be available. This too has been offered as a candidate for anthropic reasoning, and it too remains genuinely debated, without full consensus on whether it demands a multiverse explanation or a deeper, single-universe mechanism not yet discovered. Others respond that this criticism, while understandable, may be asking anthropic reasoning to do a job it was never meant to do. Under this more sympathetic view, anthropic selection isn't meant to replace deeper physical explanations where they exist and can be found. It's meant to be one additional tool, useful specifically for the subset of puzzles where a value appears to require an observer-compatible universe to exist at all, and where no other mechanism has yet been found despite considerable effort. Whether dark energy's specific value ultimately falls into that category, or whether some future breakthrough will explain it from first principles without any appeal to a multiverse at all, remains genuinely unknown, and reasonable physicists continue to disagree about which outcome is more likely. This idea, that we observe the conditions we do partly because those are the only conditions compatible with an observer existing to notice them at all, has its own name, called the anthropic principle, and it remains one of the more philosophically contested ideas in modern cosmology. Some physicists find it a genuinely useful and even necessary tool for making sense of fine-tuning puzzles that otherwise seem to demand an almost impossibly precise coincidence. Others worry that leaning on this kind of reasoning too heavily risks explaining away puzzles that might have a deeper, more specific physical answer we simply haven't found yet, substituting a kind of statistical shrug for the kind of concrete explanation that has driven physics forward at every previous stage of its history. This is where we can finally close our second open loop from earlier in tonight's journey. The question of whether space, if it had a beginning, began as a point, or was already infinite the instant it started. The honest answer, given everything we've walked through, is that the question may not even be well-formed in the way it sounds. Our observable universe had a beginning, 13.8 billion years ago, emerging from the end of inflation within one particular bubble. But if eternal inflation is correct, the larger inflating background that produced our bubble may not have a beginning at all, in any meaningful sense. It may be eternal, stretching infinitely into the past as well as the future, with our bubble being just one event within an endless, ongoing process, rather than the entire process itself. In other words, our universe had a beginning. The multiverse, if it exists, quite possibly did not. There's a further subtlety here worth sitting with slowly, because it complicates even that answer in an interesting way. Some detailed mathematical analyses of eternal inflation suggest that the process, run backward in time rather than forward, cannot actually be extended infinitely into the past after all, that there's a theorem, developed by researchers working through the underlying equations carefully, suggesting that any universe which is, on average, expanding, must have had some kind of beginning, even if that beginning isn't a single point in the way the Big Bang is sometimes pictured, but rather a boundary to the entire eternally inflating structure itself, somewhere in the deep past, before which the very concept of before may not apply in any way our current physics can describe. This means even the multiverse, under some analyses, might not be truly eternal after all. It might simply push the question of a beginning one level further back, into a still larger structure we don't yet have the mathematics to describe, the way each previous chapter of tonight's journey has pushed the boundary of everything one layer further out, without ever quite reaching a final, settled answer. Let that sit for a while. There's nothing urgent here. Just an enormous, quiet idea, settling slowly. It's worth adding one more layer to this picture before we move on, because it connects the multiverse idea to something slightly more familiar, drawn from an entirely different branch of physics. Quantum mechanics, the set of rules governing the behavior of particles at the smallest scales, has its own long-standing puzzle about what happens when a quantum system is measured. Before measurement, certain quantities can exist in what's called a superposition, a kind of blend of multiple possible outcomes at once, described by mathematics that gives each outcome a certain probability. The puzzle, debated since the earliest days of quantum theory, is what actually happens at the moment of measurement, when we observe one specific, definite outcome, rather than the blended possibility the mathematics seem to describe beforehand. It's worth sitting with an example of this superposition puzzle before moving further, because it's easy to let the phrase multiple outcomes at once slide past without really absorbing how strange it is. Consider a single unstable atomic nucleus, one that has some fixed probability of decaying within a given hour, and no way, even in principle, to predict the exact moment it will decay, only the overall odds. Before any measurement is made, quantum mechanics describes this nucleus as existing in a superposition of having decayed and not having decayed, simultaneously, with the mathematics assigning a specific probability to each outcome, rather than describing a single, definite fact that we simply haven't learned yet. This is different from ordinary uncertainty, the kind we experience in everyday life. If you don't know whether a coin sitting under a cup has landed heads or tails, you're simply ignorant of a fact that already has one definite answer, sitting there, waiting to be revealed. Quantum superposition, at least under the most straightforward reading of the mathematics, describes something stranger, a situation where neither outcome is yet definite, where the nucleus is genuinely, physically in some blended state of both possibilities, right up until a measurement forces one specific outcome to become real. The puzzle of what forces that transition, and what happens to the other possibility once it does, has been debated since the earliest decades of quantum theory, without full resolution even today. The many-branching interpretation we've been discussing proposes that nothing is actually forced or resolved at all. Both outcomes continue to occur, but from that moment onward, the version of reality where the nucleus decayed and the version where it didn't become entirely separate, non-communicating branches, each one complete and internally consistent, each one containing its own version of you, the observer, having witnessed one specific, definite outcome, with no awareness that another version of the same event, and another version of yourself, is unfolding in a branch you can never access. Scaled up across the entire history of the universe, with countless quantum events occurring constantly at every scale, every moment, this interpretation implies an almost unfathomably vast branching structure, far exceeding even the enormous scale of the bubble universe multiverse we discussed earlier in this chapter, not scattered across some larger inflating space, but laid directly on top of our own reality, branching continuously, silently, undetectably, at every measurement that has ever occurred or ever will. One proposed answer, developed in the middle of the 20th century and still taken seriously by a meaningful fraction of physicists today, suggests that measurement doesn't collapse the superposition into a single outcome at all. Instead, every possible outcome continues to occur, but in separate, non-communicating branches of reality, each one just as real and complete as the others, with the observer in each branch simply experiencing the one outcome consistent with their own particular branch, unaware that the other outcomes are unfolding in parallel, elsewhere, in branches they can never access or detect. This is a completely different flavor of multiverse from the bubble universes produced by eternal inflation. This one arises from the mathematics of quantum measurement rather than the mathematics of cosmic expansion, and the other universes it proposes are, in some sense, laid directly on top of our own, branching at every quantum measurement, rather than existing as separate bubbles scattered through some larger inflating space. Whether either of these ideas, or both, or neither, turns out to accurately describe reality remains genuinely unresolved, debated actively among serious researchers who often land in quite different places depending on which puzzles they find most pressing and which kinds of explanations they find most satisfying. What's worth sitting with, gently, is simply the fact that the universe might not be the whole of everything, is not a single, isolated speculation confined to cosmology alone. It emerges, independently, from at least two genuinely separate branches of physics, arrived at through entirely different lines of mathematical reasoning, for entirely different reasons, and yet converging on a broadly similar theme, that what we experience and measure might be one slice of something far larger, with the rest permanently, structurally beyond our direct reach. We've spent a great deal of tonight moving outward, layer by layer, from the observable horizon, to the larger unreachable universe beyond it, to a possible infinite background of eternally inflating space producing countless other universes entirely, and even to a second, entirely separate kind of multiverse arising from quantum mechanics itself. At every step, we've assumed that beyond is a meaningful direction, that there's a there out there, waiting, even if we can never reach it or see it. Now let's slow down and ask something quieter, and in some ways stranger than anything else tonight, does that assumption even hold up? This is where we can finally close our third open loop, the question of what it even means to say something exists, if it's forever unreachable and unobservable, by any process, for the rest of time. There are, broadly, two ways physicists and philosophers of science tend to approach this question, and it's worth walking through both slowly, without rushing to pick a winner, because reasonable, serious people land in different places here. The first approach says that existence and observability are, in principle, entirely separate questions. Something can be real, can genuinely exist, without us ever being able to detect it, the same way a book sealed permanently inside a vault, never to be opened again by anyone, still contains real words on real pages, even though no one will ever read them again. Under this view, the galaxies beyond our cosmic horizon are exactly as real as the ones we can see. Our inability to observe them is a limitation of us, not a limitation of their existence. The second approach is more cautious, rooted in a philosophy of science that's wary of making strong claims about things that can never, even in principle, be tested or verified. It's worth sitting with why this cautious position has real force, rather than treating it as simple stubbornness or a refusal to think big. Science has historically made its most reliable progress by proposing ideas that could, at least in principle, be shown to be wrong through observation or experiment, a standard sometimes called falsifiability. A claim that can never be tested, never confirmed, and never ruled out by any conceivable measurement sits somewhat awkwardly against that standard, however elegant or mathematically compelling the reasoning behind it might be. This doesn't necessarily make the claim false. It simply places it in a different category from claims that have been, or could someday be, directly checked against reality, closer, in some respects, to a metaphysical position than a strictly scientific one, even when it emerges from genuinely rigorous mathematical physics. Under this view, a claim like there are infinite other universes beyond ours sits in an uncomfortable space. It might be true, it might be a beautiful and elegant mathematical consequence of theories that explain other things very well, but because it can never be confirmed or ruled out by any possible observation, some scientists are hesitant to call it a scientific claim at all, in the strict sense, as opposed to a kind of philosophical or mathematical extrapolation that happens to be dressed in the language of physics. Neither of these positions is wrong, exactly. They reflect a genuine, unresolved tension in how we think about knowledge itself, what it means to know something, versus what it means for something to simply be true, whether or not anyone could ever come to know it. It's worth walking through a specific, concrete example of this tension, because it can feel a bit abstract described only in general terms. Consider a particular galaxy, one that crossed beyond our Hubble radius many millions of years ago, its recession speed now exceeding the speed of light, its future light permanently unable to reach us no matter how long we wait. Does that galaxy still exist, right now, at this very moment? Under the first view, the answer is obviously yes, of course it still exists, continuing to evolve, its stars living and dying, entirely unaffected by whether anyone on Earth can see it. Under the second, more cautious view, the honest answer is that the question itself may not be fully well posed, because right now, at this very moment, for an object so far away that no signal could ever connect it to us, isn't a straightforwardly meaningful phrase in the framework of relativity, where simultaneity between distant, causally disconnected points isn't the simple, universal concept our everyday intuition assumes it to be. It's worth walking through this idea of relative simultaneity with a slightly more concrete picture, because it's one of the genuinely strangest features of relativity, and easy to state without really absorbing. Imagine two observers, moving at different, constant speeds relative to each other, both trying to determine whether two distant, widely separated events happened at the same time. Under Newton's older picture of physics, this would be a simple, objective question with one correct answer, agreed upon by every observer regardless of their own motion. Under Einstein's relativity, it isn't. Two observers moving differently relative to each other can genuinely, correctly disagree about which of two distant events happened first, or whether they happened simultaneously at all, not because one of them is mistaken or has incomplete information, but because simultaneity itself, for spatially separated events, isn't a single, universal fact built into the structure of the universe. It's a relationship that depends on the observer's own state of motion. For events happening close together, and for observers moving at ordinary, everyday speeds relative to each other, this effect is fantastically small, far too tiny to ever notice in daily life. But it's not a rounding error or a philosophical curiosity, it's been confirmed through extremely precise experiments, and it becomes conceptually unavoidable once you're dealing with the kind of vast distances and the kind of relative motion involved in cosmic expansion. For a galaxy so distant that no signal could ever connect it to us, asking what it's doing right now runs into exactly this difficulty. There may be no single, privileged answer to that question at all, only a range of equally valid answers depending on which observer, moving in which direction, is doing the asking. This connects to a genuinely deep and somewhat unsettling feature of Einstein's physics that we haven't yet touched on tonight. The very idea of the same moment across vast distances is more slippery than it first appears. In relativity, whether two distant events happen at the same time can depend on the motion of the observer making the judgment, in a way that has no single, universally agreed answer once large distances and relative motion are involved. For nearby events, this effect is too small to matter in any practical sense. But for events separated by the kind of cosmic distances we've been discussing all night, the question of what's happening right now in some far-off galaxy, permanently beyond our horizon, may not have a single, well-defined answer at all. Different equally valid reference frames could disagree about what counts as simultaneous with this exact moment, here, tonight. Here's a way to hold this gently, rather than trying to resolve it firmly one way or the other. The mathematics that predicts a larger, unreachable structure beyond our horizon, inflation, the shape of an infinite flat universe, eternal bubble universes, even the quantum multiverse, is the same mathematics that has made extraordinarily precise, verified predictions about things we can measure. The temperature patterns in the cosmic microwave background. The large-scale distribution of galaxies. The abundance of light elements formed in the earliest minutes after the beginning. These are not vague, hand-wavy ideas. They are rigorous frameworks that happen to also predict things beyond our ability to ever check. So we're left in a strange, quiet position, trusting a mathematical framework because it gets so much right about the world we can measure, while accepting that some of its most sweeping predictions, an infinite universe, an eternally inflating multiverse, branching quantum realities, might be permanently, structurally beyond our ability to confirm, one way or the other, forever. That's not a failure of science. It's closer to a boundary of what any observer, anywhere, embedded inside a universe, could ever hope to know about the whole of which they are a part. There's something almost comforting in that limitation, if you sit with it the right way. It means the universe is not obligated to make itself fully knowable to the things living inside it. It can be larger than any observer within it could ever map, and that's not a flaw in the observer, or a flaw in the universe. It's simply the shape of the situation. Earlier tonight, we asked whether there's any loophole at all, any way, even in principle, that we might one day glimpse something beyond our own cosmic horizon. It's time to close that loop gently, because there is, in fact, one candidate, even if it remains speculative and unconfirmed. If eternal inflation is correct, and our universe is one bubble among countless others, there's a theoretical possibility, explored seriously by a number of physicists, that two bubble universes could occasionally collide, one region of ended inflation bumping directly into another, somewhere in the vast inflating background between them. If such a collision happened early enough in our universe's history, and if we happen to be looking in the right direction, it could, in principle, leave a very faint, very specific pattern imprinted in that oldest light we've discussed at length tonight, the cosmic microwave background. It's worth understanding, a little more carefully, why a bubble collision would leave a roughly circular mark at all, rather than some other shape, because the geometry is actually fairly intuitive once you picture it correctly. When two expanding bubbles collide, the disturbance from the collision travels outward from the point of contact at a finite speed, spreading across the surface of our own bubble universe from that specific location. By the time we observe it today, embedded within the much larger and more ancient light of the cosmic microwave background, the disturbance would have had billions of years to expand outward across the sky as seen from Earth, appearing not as a single point, but as a roughly circular or disc-shaped patch, its exact size and position depending on where and when, in our universe's early history, the hypothetical collision actually occurred. This means the search isn't looking for something at a single predicted location, the way an eclipse can be predicted down to a specific time and place. It's a broad search across the entire sky, looking for any statistically significant disc-shaped anomaly, of any size, anywhere, that differs from the surrounding pattern in a way specifically consistent with a collision signature rather than ordinary random variation. This means the search isn't looking for something at a single predicted location, the way an eclipse can be predicted down to a specific time and place. It's a broad search across the entire sky, looking for any statistically significant disc-shaped anomaly, of any size, anywhere, that differs from the surrounding pattern in a way specifically consistent with a collision signature rather than ordinary random variation. It's worth adding, gently, that this kind of open-ended, whole-sky search represents a particular kind of scientific patience worth admiring on its own terms, independent of whether it ever succeeds. The researchers involved know, going in, that a positive result is unlikely, that most or all of their careful work may end in a null finding, adding one more line to the long list of places a bubble collision signature has been searched for and not found. And yet the search continues, refined with each new generation of measurement, because the alternative, simply assuming the question is unanswerable and declining to look at all, would mean giving up on the one concrete opportunity physics has ever proposed for testing an idea this vast, this quiet, and this far beyond our ordinary reach. The proposed signature of such a collision would be a roughly circular disc-shaped disturbance in the temperature map of that ancient light, a region where the temperature pattern differs subtly from the surrounding sky, in a way consistent with the specific physics of a bubble collision rather than the ordinary statistical fluctuations that produce the rest of the map. Several research teams have, in fact, searched carefully for exactly this kind of pattern, scanning the full sky data gathered by satellite missions for any sign of such a disk, using statistical methods designed to distinguish a genuine collision signature from the kind of pattern that could arise by chance from ordinary random noise. So far, no confirmed signal of this kind has been found. Some candidate patterns have been proposed in early analyses and later shown, on closer statistical scrutiny, to be consistent with ordinary noise rather than genuine evidence of a collision, an important and honest part of how this kind of research actually proceeds, where promising-looking candidates get tested rigorously and, more often than not, fail to hold up once examined more carefully. The search continues, quietly, in the background of ongoing cosmological research, without much public attention, because a null result, finding nothing, doesn't make for dramatic headlines, even though the search itself represents something remarkable, an actual, real attempt to test, however indirectly, whether something exists beyond the one universe we've always assumed was the whole of everything. This is, as far as anyone currently knows, the only proposed method by which evidence of anything beyond our own universe could ever reach us. It requires very specific, favorable conditions, an early collision, positioned just right, leaving a signal strong enough to survive nearly 14 billion years of subsequent cosmic evolution without being washed out by everything that happened afterward. It may never produce a confirmed result. But its mere existence, as a real, testable hypothesis rather than pure philosophical speculation, is itself a remarkable thing to sit with as we move toward the closing portion of tonight's video. It's worth noting, gently, that even a confirmed detection of such a collision signature wouldn't tell us everything we might want to know. Sit with the strangeness of that limitation for a moment, because it's worth appreciating on its own terms. Even in the most optimistic scenario, a clear, confirmed, statistically undeniable signal, found tomorrow, in the data we already have, the discovery would answer only the narrowest possible version of tonight's question. It would confirm existence without confirming character. It would tell us something is out there, without telling us anything at all about what it's like to be there, what rules govern it, whether time even flows the same way within it, or whether anything resembling wonder, or rest, or a quiet voice describing the night sky, has ever occurred within it at all. We would gain a fact, and lose almost none of the mystery. It would confirm that at least one other bubble universe exists, or existed, somewhere nearby in the larger inflating structure. But it wouldn't tell us what that other universe was like inside, whether it had different physical constants, whether it formed stars and galaxies of its own, whether anything resembling an observer ever arose within it to wonder about its own horizon, the way we've spent tonight wondering about ours. It would be a knock on a wall we already believed was there, confirming something is on the other side, without ever letting us open the door and look inside. We may never see beyond our horizon directly. But we haven't entirely given up trying, even if the attempt looks, for now, like searching for a single very faint bruise across the entire visible sky, left behind by something that may have happened before galaxies, before stars, before almost everything we've spent tonight discussing, ever came to exist at all. There's a final thought worth sitting with here, before we move into the closing passage of tonight's journey. Every method we've discussed across both parts, measuring redshift, mapping the cosmic microwave background, surveying galaxy positions, searching for the faint imprint of a bubble collision, shares something in common. Each one takes something impossibly distant, impossibly old, or impossibly abstract, and turns it into a number, a pattern, a map, something a careful, patient person can actually work with, night after night, year after year. The universe doesn't make itself easy to study. It simply sits there, vast and mostly silent, and it's only through this accumulated, careful labor, measuring, comparing, doubting, remeasuring, that any of tonight's story became knowable at all. That's worth remembering the next time you look up at an ordinary night sky, away from any city lights, and see what looks like nothing more than scattered points of light on a dark background. Every one of those points carries, folded inside it, the entire story we've spent tonight unfolding, a horizon behind a horizon, a bubble within an ocean of bubbles, a question that may never close, resting quietly overhead, waiting for nothing in particular, least of all an answer. There's one more thread worth gathering up before we let everything rest, because it ties both parts of tonight's journey together into a single, quieter shape. Everything we've discussed, across both parts, has really been variations on a single idea, approached from different directions each time. A boundary defined by the age of light, rather than by any physical wall. A boundary defined by the composition of the universe, mostly hidden from direct detection. A boundary defined by mathematics, in the shape of an infinite flat geometry we can measure but never fully traverse. A boundary defined by the very process that seeded our own universe, potentially producing endless others we can never visit or confirm. And finally, a boundary defined by observation itself, the unsettling possibility that some questions about beyond may not have single, well-defined answers at all, once you follow the physics carefully enough. Every single one of these boundaries shares the same basic shape, even though they arise from entirely different areas of physics, discovered by entirely different people, across nearly a century of careful, patient work. They are all horizons, not walls. Edges of what we can currently reach, or measure, or confirm, never edges of what actually exists. And every time humanity has pushed against one of these horizons, the picture that's emerged on the other side has turned out to be larger, not smaller, than what came before. Larger than a single galaxy. Larger than a single universe. Perhaps larger than the very idea of a single, countable everything can meaningfully describe at all. There's a kind of quiet comfort available in that pattern, if you're willing to sit with it rather than resist it. It suggests that not knowing, in this particular domain, isn't a temporary embarrassment waiting to be fixed by the next generation of telescopes or the next clever piece of mathematics. It may be a permanent, structural feature of what it means to be any observer at all, embedded inside a universe large enough to contain the observer doing the observing. We are, each of us, a small, local reading, taking measurements from one particular room in a house whose full size we may never determine, and that's not a failure of the measurement, or a failure of the house. It's simply the shape of being somewhere, rather than everywhere, inside something this large. Let's bring everything we've covered across both parts of tonight back together, gently, one more time, without adding anything new, just letting the shape of it settle fully. We began with a number. 93 billion light-years, the width of everything we can see. And we learned, slowly, that this number describes a horizon, not a wall, a boundary drawn by time and the speed of light, not by the edge of space itself. It's worth pausing, one final time, on how strange it is that a single number like that can carry so much inside it. 93 billion light-years sounds, on its own, like a simple measurement, a distance, plain and complete, the way you might measure a room with a tape and be done with it. But we've spent this entire journey discovering that the number is really a kind of doorway, and everything interesting sat on the other side of it. The fact that it marks a horizon rather than an edge, the fact that most of what fills it is invisible to us in composition rather than merely distant, the fact that whatever lies past it may repeat endlessly, or branch endlessly, or simply continue in ways our mathematics can describe but our instruments can never confirm. We followed that horizon backward through history, from solid crystal spheres holding up an ancient sky, to a 200-year-old paradox about why the night sky is dark at all, to the modern, expanding universe we now take for granted, barely a century old as an accepted scientific fact. We learned that almost everything filling this vast volume is something we still cannot directly detect, a hidden 95% of everything, made of dark matter and dark energy, shaping the structure and expansion of the cosmos from behind a curtain we've only recently learned exists at all. We discovered that some of the light reaching us tonight is the last light we will ever receive from certain galaxies, forever slipping beyond a boundary called the Hubble radius, their distance from us growing faster than light itself can ever cross. We considered the strange, quiet possibility that our entire universe, everything we've discussed across both parts of tonight, every galaxy, every star, every horizon, might itself be a single bubble, floating within an eternally inflating background that may or may not have a beginning of its own, endlessly producing other bubbles, other universes, forever, in every direction. And we noted that an entirely separate branch of physics, quantum mechanics, arrives at its own, different kind of multiverse, through entirely different mathematics, for entirely different reasons. We sat with the deepest question underneath all of it, whether something can be said to exist at all, if no observer, anywhere, at any point in the entire future of the universe, could ever confirm it. And we found one fragile, speculative loophole, a faint bruise that might be hiding in the oldest light in the sky, left behind by a collision between our universe and another, still unconfirmed after years of careful searching. There's no need to resolve any of it tonight. There's no need to resolve it ever, really. It's worth sitting with why that's not a disappointing place to end, even though it might sound like one described plainly. An answer, tidy and complete, would close the story. It would let the mind file the question away, satisfied, finished, ready to move on to something else entirely. What we have instead is something quieter, and in its own way, more durable, a question large enough to outlast any single answer, one that can be picked back up on another night, from a slightly different angle, without ever feeling used up or resolved. That kind of open question is, in a strange way, more restful than a closed one. It asks nothing further of you right now, and it will still be waiting, exactly as vast, whenever you next think to look up. Some questions are meant to be held, gently, rather than answered, carried quietly, the way you might carry a very old, very heavy stone that you've stopped trying to lift, and instead simply rest your hand against, feeling its weight, its coolness, without needing it to become lighter. The universe, however large it turns out to be, however many bubbles, however many horizons stacked one behind another, forever, is not asking you to understand all of it tonight. It never has been. It only asks that you exist inside it, for a while, looking up occasionally, wondering, and then letting the wondering soften into rest. So, what lies beyond everything we can see? The honest answer, after everything we've walked through tonight, across both parts of this long, slow journey, is that we don't fully know, and we may never know, not because we haven't looked hard enough, but because the universe itself may have built a horizon into its own structure that no observer, anywhere, could ever fully see past. Maybe it's more of the same, more galaxies, more stars, stretching out in every direction without limit. Maybe it's something else entirely. Other bubbles, other universes, governed by rules we've never encountered and never will. Maybe the question doesn't even have a final answer, the way some questions simply don't. What we do know is this: everything you've ever seen, every star, every photograph from every telescope, every number quoted about the size of everything, is a horizon. Not a wall. A horizon, the edge of what light has had time to bring us, in the brief, quiet window we happen to be alive in. And somewhere past that horizon, whatever is or isn't there, the universe continues on, indifferent to whether anyone is watching, or wondering, or drifting off, right about now, into sleep. Sit with it a little longer, if you're still here, still awake enough to notice. There's no expectation attached to that either. The universe has been sitting here, patiently, for 13.8 billion years, and it will go on sitting here, indifferent and enormous, long after tonight's video ends, long after this particular question fades from your mind into something softer, quieter, less shaped like a question at all. Good night.